We're going to take a look at chapter 5 from year 2 pure, which is radians. And radians are just a different way that you can measure turning. Okay, so what do I mean by that? Well, you will be used to the idea that this, for example, is 90 degrees, but you might have wondered why and just taken that for granted. Sure, it's connected to the idea that there are 360 degrees in a full turn, but again, that's a fairly arbitrary distinction to make. So we can call this 360 degrees, we can call this one turn, and there are other ways that we can define this amount of turning. Okay, and that's what a radian is. So in this chapter, we're going to look at moving between degrees and radians. So what is 45 degrees in radians? Something like that. Then we're going to use some formulae that we can we can change existing things like pi r squared and so on to work in radians and find arc lengths. Arc lengths are sort of the curved parts of circles. Sector area, well, a sector is a piece of a circle made by going into the radius of the center. Okay, something like that would be a sector area. We can start solving trig equations like our year 12 sort of trig in radians instead of degrees. And finally, something that's quite different and is really foundational for other ideas later on is something called small angle approximation, which will be a new idea. Okay, so this one here is a degree. Of course, that's more than 1 degree, but roughly it's a 360th of a circle. This is 1 radian. Okay, and a radian is defined as the amount of turning necessary such that the length of the radius is actually equal to the arc length. Okay, so if you just think about turning, there must be some sort of particular point where once you turn so much, those numbers are the same. And we call this point, 1 radian of turn that achieves that. Okay, so how many of these radians will go into a circle? Well, think about r on the outside. How many r's go together to cover the circumference of a circle? Actually, you know this already. The circumference is made up of how many r's? It's made up of 2 pi r's, a little bit over 6 2 pi. Okay, so we're going to say then that 360 degrees is called 2 pi radians. Notice we don't have the degree symbol. We don't say degree, we say 2 pi radians. Okay, and this is sort of a benchmark that we can use to do other conversions. Why would we do this, you say? Well, later on when we do some differentiation, when we learn how to differentiate more complex things, we can actually only differentiate when we define in terms of radians, and we'll look at why that is later. That's one of the reasons we will do this. So if 2 pi radians is 180 degrees, if 2 pi is 360, then 1 pi must be 180. How do you move between them? On a simple level, you could sort of say the number disappears. So you're dividing by 180 because the number is just 1, it's sort of not there. And at the same time, pi appears. So it's probably more useful to write something like this. Divide by 180 and pi appears. So something like this. Okay. And the other way around, well, the other way around must be dividing by pi over 180, and keep flip change says that that's the same as 180 appearing over pi. Okay, in practice, you probably won't do this. What you will do is you will benchmark it to 180 degrees in pi. So what do I mean by that? So if 180 is pi radians, well, half of that will be half of pi over 2 radians. And in reality, this is what you'll probably do. What about this? Pi over 3. Think of pi as being 180. The 180 is to be divided by 3, so it's 60. Okay, just pause the video here for a moment and have a quick think about what the equivalence would be moving between degrees in radians and radians in degrees. You can do this with a calculator if you like, but you may find it's actually easier to just sort of connect things to 180 and pi. Okay, so assuming you've done that now, you should get these numbers here on the board. And these are numbers that you're going to see quite a lot, especially all of these ones here. Okay, so please be on the lookout for them, because 30, 45, 60, 90, all in terms of radians, is going to happen from here on out. Okay, so questions might be in degrees, they might be in radians, and we'll talk about how you spot that in a moment. Okay. If we're sketching graphs with radians, well, what do we change? We just change 90 to pi over 2, and 180 to pi, and so on. Okay, so if we draw this as the same scale, we're effectively just changing these numbers. But x is no longer in terms of degrees anymore. Okay, this would be in terms of radians. Tan would be the same sort of thing as well. So what would cos of x plus pi over 2 look like? At this point, you will just think, well, that's the same as 90. I know that an addition inside the function with x has the sort of opposite effect to what you expect. So we're going to the left. Plus and minus means a translation. We're moving the graph to the left by 90. If that's what an original cos graph looks like, well, it's going to sort of move to the left by 90. So I'm thinking 0. Yeah, 0 in this part here. A little bit hard to compare, because actually my dotted line was the same as their solid line, but you can see we've shifted this way. Okay. So some quick questions. Let's have a think. X plus pi. So again, this is left by 180 degrees. So if you draw the original, okay, that's 90, that's 180. So it's a little bit like it's going to start there instead. 2x minus pi over 2. So two transformations here. 2x, what effect would that have? Well, if this is 90 normally, and 180 and 270 and 360, it's going to stretch by scale factor a half. So it's going to become sort of more cramped. So one little trick you could do is, instead of calling that 90, you could call that 45. So you could do, let's say 45, yeah. So you could have pi over 4, pi over 2, and you could actually just sort of extend the graph this way. That's one way that you could do that one. And this one here, again, sort of the same thing. So stretching it, so instead of 1 to minus 1, it would be 2 to minus 2, and to the left by 45 degrees. Okay, what else changes? Well, everything that you sort of learn about rules of symmetry for sine and cosine and so on, repetitions for sine, cos, and tan, they all have radian equivalents. So for sine, you might remember that you could do 30 or 150 to get the same output. Well, instead of doing that now, if we have 30, for example, 30 is the same as pi over 6. So you don't have 30 and 150 as your answers, adding to 180, like you did in year 1. You would have pi over 6. And I like to think 180 is the same as pi. So what's the partner with pi over 6 that makes them both add to pi? Well, it's 5 pi over 6. Pi over 6 in from the left, pi over 6 down from 1 pi gives you 5 pi over 6. Okay, so these same sort of connections from before about reflectional symmetry and so on can be used. And there's just some examples for you on the board. You might wish to change radians into degrees as you're starting out, but as you do this more and more, you will actually get quite comfortable working with radians probably. One thing to note, super important, okay, very, 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 very important. If you are going to be using things like sine, cos, tan, inverse sine, all this sort of stuff, if you are working in radians mode, you need to change your calculator's angle unit to be R. And at the top of your calculator, it will say R once you're in radians. It will probably be in D mode at the moment, which is degrees. So you must make sure your calculator is in the right mode. If you don't, it can really cause lots of issues and all your working out is sort of nonsense. So please make sure you're working in the right mode. And there we go. That takes us to 5a and 5b. So you should spend plenty of time now practicing moving between degree form and radians form.